Assalamualaikum dan selamat sejahtera. My name is Muhammad Adam bin Baharuddin from Group 7. I'm going to present about my part, which is introduction. Solid mechanics course introduce the principles of displacement, strain, stress, and constitutive equations of elastic solids in 1, 2, and 3 dimensions. The first real-life problem definition is detailed and provides guidelines for the design team to follow. The second definition may be appropriate in some circumstances, but it may allow the designer too much leeway. Because the problem definition was too ambiguous or inaccurate, the resulting product may not accurately match the needs of the consumer, yet it may still fit the problem description. To solve real-life problems, search for creative solutions by brainstorming, checklist, attribute listing, force relationship techniques, and different point of view. Hence, in this project, we are going to implement relevant approach required in this course to tackle an engineering-related challenge. Thank you.
Okay, Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Mirzwan. I would like to present about analysis. Okay, first, stress-strain analysis. Stress and strain in an axial solid and hollow bars. This example was used to demonstrate the application of axial stress, axial strain, and modulus of elasticity. The instructor started by going through the definition and equation for axial stress and strain and talking about stress and strain plot and modulus of elasticity. The students had just started to lose interest, so the instructor then dangled an iPod by the earphone and passed out small pieces of wire to each of the students, with some of the insulation stripped off. A brief discussion was then initiated about what kinds of materials make up headphone wires and what magnitude of force it takes to break the wires. The discussion was concluded with the fact that both the copper wire and insulation actually deform together. Okay, this is the equation that used in the problem. The second one is the deflection of beam. Structures such as building and bridges consist of a number of components such as beams, columns, and foundation, all of which act together to ensure that the loadings the structure carries is safely transmitted to the supporting ground below. Normally, the horizontal beams can be made from steel, timber, or reinforced concrete and have a cross-sectional shape that can be rectangular, T or I shape. The design of such beams can be complex, but is essentially intended to ensure that the beam can safely carry the load it is intended to support. This will include its own safe weight, the weight of the structure it is supporting, and what is often referred to as live load. For example, the weight of people and furnishing in building, or the weight of road or rail traffic in bridges. Example of the beam is shown below. Okay, this is the picture shows the beam. Next, calculation beam deflection requires knowing the stiffness of the beam and the amount of force or load that will influence the bending of the beam. We can define the stiffness of the beam by multiplying the beam's modulus of elasticity by its moment of inertia. The modulus of elasticity depends on the base beam material. Okay, this is the example. Okay, the third one is the column buckling. Okay, as we can see, figure 3a depicts the long narrow pin-ended rod on which the compressive force is loaded along the symmetrical axis. Taking into account the principle of initial imperfection of the rod, the rod is bent during the load by the axial force, like figure 3b, in order to reveal the internal bending moment. It is necessary to cut the column in the middle zone for creating the free body diagram, like the figure 3c. Okay, figure 3 shows the long slender pin-ended rod column. Design scheme of a compressed pin rod, buckling of a slender rod C, free body of Euler buckling model. Moment equilibrium dictate that the bending moment is given by M equal to N negative N Y. Here Y is the lateral deflection from the resistance of material. It is known as this equation. The above two relationships provide defining differential equation for Euler buckling. In addition, according to the Nagy method, the compressive force reaches its critical value when the end of the rod approach each other, and the work performed by external forces is equal to the deformation work of the bending of the compressed rod. By solving it, the formula of calculating critical force/stress was developed by Leonard Euler. The equation is like in the picture. Okay, next, the fourth one is the strain energy. The strain energy produced by bending is usually large in comparison to the other forms. When a beam bends, layers on one side of the neutral axis are stretched and on the other side they are compressed. In both cases, this represents stored strain energy. Consider a point on a beam where the bending moment is m. Now consider an elementary layer within the material of length dx and thickness dy at distance y from the neutral axis. The cross-sectional area of the strip is dA. The bending stress is 0 on the neutral axis and increase with the distance y. It is tensile on one side and compressive on the other. If the beam has a uniform section, the stress distribution is as shown in the picture below. The volume of the strip is dx dA. The strain energy in the strip is part of the total, so du equal to just like the equation. Okay, the last one is the thick cylinder. The stress state of thick wall cylinder granite specimen under 3 axial compression are changed by their pores. Figure 3 shows the distribution under confining pressure. In my left is the picture of 3A and in my right is the picture of 3B. At each point of the specimen, the stress can be expressed as the equation in the picture. Okay, according to equation 1 and 2, decrease as R increase, while assuming that the failure of the thick wall cylinder satisfies the column criterion. As the specimen diminishes, its bearing capacity just reach the maximum value. The 3 axial compressive strength can be expressed as equation below. Okay, we can see the relationship between Fn and N shown in figure 4 below. According to figure 4, Fn is always less than 1. The intermediate principal stress has a great influence on the strength of the rock specimen. According to the twin shear strength theory, the intermediate principal stress affects the peak TCS as follows. Okay. According to equation 9, the peak TCS of each point on the inner wall has no relation with its radial position. It is only related to the ratio of internal and external pore size. Therefore, if the reflection effect of the metal is constant and the confining pressure keeps the same, the axial bearing capacity of the cylinder will be higher than of the complete specimen. However, the test results are not the same as the prediction in equation above. Okay, that's all from me. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Hafiz bin Azwan, AD190106, and today I will discuss about the calculation. So the first one, from 5 real world problem that we found, our group choose second problem, which is from topic 2, deflection of the beam, as the subject of the study. In this problem, we try to write the moment equation by using singularity function, trying to integrate to find the deflection equation and calculate the deflection at the free end of the beam as shown below. Data given: modulus of elasticity E equal to 200 GPa, area of moment of inertia for the cross section I equal to 130 times 10 power of 6 millimeter power of 4. So the figure shows like this. And step 1, we try to label free body diagram. We put the MR and AY in the diagram. So step 2, find the AY direction and MR, which is sum of Fy, and we found out AY equal to 65 kN and the MR equal to 95 kN per meter. So step 3, we write the moment equation by using singularity of function. So we put the number into the formula. Then step 4, we integrate to find the deflection. We integrate the equation. Then we integrate again to find the deflection of equation. After that, we try to find after the integrate, we try to find the deflection equation, and the final answer is y3 equal to negative 6.97 millimeter per second. Alright, that's all from me. Thank you.
Assalamualaikum and good day. My name Alif Ikram bin Nur Azmi Tarmizi, metric number AD190097. So I will be presenting the discussion for my group project. So for discussion, beam deflection usually refers to the state of deformation of a beam from its original shape due to load or force that acting on the beam, either uniformly distributed or a concentrated load. Generally, through the application of beam deflection theory, several equations can be obtained from which the accurate values of beam deflections can be determined in various practical cases. Furthermore, deflections are also utilized in the analysis of statically indeterminate beam. There are several methods that can be used to determine beam deflections, including double integration method, moment area method, Macaulay's method. So in this case, our group has chosen the Macaulay's method to use as a solution to the engineering problem. Macaulay's method basically refers to a technique to discover the equation that defines the deflected shape of a beam. So it also allows us to inscribe a single equation involving the bending moment for the full length of any beam. Generally, the double integration method are only used if the load acting on it, there's only a single load acting on the beam, while Macaulay method specifically used when there are multiple loads acting on the beam. So from these equations that we gain from Macaulay's method, we can integrate the expression for bending moment using the double integration methods. Furthermore, when the value inside the bracket in the function is 0 or negative, Macaulay's method led us to turn off a partial of moment function. As we can see here, this is the Euler-Bernoulli beam theory, where the EI, where there is EI d2y over dx square equals to m, where y refers to the deflection of the beam and m is the bending moment of the beam. So afterwards, this equation could be integrated twice in order to determine the deflection. Only if the m is only if the bending moment is given as a function of x. So for most loadings, m moment could be defined as m equals to m1 times x plus p1 bracket of x minus a1 plus p2 bracket of x minus a2 plus p3 bracket of x minus a3 and so on. Where p bracket of x minus a refers to bending moments due to point loads. And these brackets of x minus a is called the Macaulay bracket. So this Macaulay bracket can be defined further as Macaulay bracket in range of 0 if x minus if x is less than a, while x minus a if the value of x is greater than a. There are two product of the integration of p bracket of x minus a, whereby this is the general method and this is for the Macaulay's method. So in Macaulay method, the moment function only will be considered at end of the section, such as for a concentrated load on a pin connected beam. So the expression can be given as p times x minus a to the power of 1. While for uniformly distributed beam, the moment can be defined as w bracket of x minus a squared over 2. While the moment at the center of the beam can be refined as m naught times x minus a to the power of 0. So that's all from me. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Iqbal bin Ismail and my matrix number is AD1900181. Okay, I would like to continue the presentation. Now I would like to talk about the conclusion. In conclusion, chapter 2 deflection of beam is where we learn to calculate the deflection of beam when force is acting on the either uniformly distributed or concentrated at any point. A few methods can be used to calculate the deflection of beams, such as double integration method, moment area method, and Margulis method. We have shown an example of calculating the deflection beam using one of the calculation method, which is Margulis method. Based on the example calculation, we have decided that Margulis method is the best method to solve the problems, and it only needs 4 steps to solve the engineering problems and find the deflection of the beam. The steps are: construct free body diagram, find the support reaction and moment, write the moment equation using singularity of function, and integrate to find deflection. Lastly, to solve problems in this chapter, it requires the ability to analyze the beam, construct free body diagram, and understanding the formula needed. That's all for me. Thank you.